Hello, everybody. Today we're talking about postulates and proofs. So this is lesson 2.5, the first of lesson 2.5. We're really just going to be talking about what the postulates are, what the proof process looks like overall, and maybe we'll do our first example of a proof that's not just purely algebra. Okay. First, a warm-up. So in this warm-up, I would like for you to maybe pause the video. What you're determining is simply whether the conclusion that's given is valid or invalid. So you might be using some deductive reasoning here. Number 4 is not that kind of example. For that one, you're just answering the question. So I'm going to give you a moment to pause. And I'm going to go ahead and fill in our answers here. So number 1, given information is angle A and angle B are supplementary. And the conclusion that they are, let's see, measure of angle A. I think this is supposed to say, I hope your notes say this, a measure of angle A plus angle B equals 180 degrees. If we make that correction, we would say that this is a valid conclusion. This is based on our definition of supplementary. For number 2, polygon RSTU has 4 sides. The conclusion that polygon RSTU is a square, that's invalid. That would be invalid. We don't have enough information. The definition of a square is going to be more complicated than just 4 sides, so this would be invalid. Okay, number 3, angle A and angle B are congruent. The conclusion that angle A and angle B are vertical angles is again invalid. You can think about some counterexamples, perhaps, really both for number 2 and 3. Of course, we could have some rectangle. That could be our polygon RSTU. And for number 3, we could have angles that are congruent and just aren't vertical to each other. They don't have to be vertical in order to be congruent. Of course, if this were flip-flopped, if I knew that they were vertical angles, then I would be for sure able to say that they are congruent. But that relationship doesn't necessarily go both ways. How many non-collinear points define a plane? Well, that would be 3. See 3 points in the name of a plane, and we only need 3, again, non-collinear points to define one. Okay. So let's go ahead and define postulates. So a postulate, let's switch colors here. A postulate, I'm going to talk about these a lot, is a statement that is accepted as true without proof. So these could be perhaps basic ideas that we've already learned that we know about points, lines, and planes. We're going to state them, restate them really, as formal postulates. We'll introduce over the course of the year other postulates as well, though. Now, memorizing these ideas, but not necessarily the exact wording, is important. We want to know the ideas. We don't care about the exact wording. You'll also perhaps notice that the book gives these postulates like numbers. It assigns numbers to them, like postulate 1.2 or something like that. The numbers are not important either. The exact wording, the numbers, not stuff that's important for us. But the actual statements, the ideas themselves, that's going to be very important to know in the future. Okay, so let's see what they actually are. The first one we'll talk about, and this should sound really familiar, through any 2 points, there is exactly one line. Through any 2 points, there is exactly one line. Now, an example of this is given at the right. So we have some line N, and it is the only line that would ever go through points P and R. That's what our phrase exactly means back over on the left. There can't be 2 different lines that go through two particular points, just one. We could name it in a couple different ways. We could call this line PR or line RP, but it's the same as line N. Okay, next one. Through any 3 non-collinear points, there is exactly, there's that word again, one plane. We could again name that plane differently, but it's just going to be the same plane. Our example shows our plane K or plane ABC or CBA, whatever we want to call that plane over there. Excuse me, it is the only plane through the non-collinear points A, B, and C. Okay. Now, the next postulate is going to sound maybe repetitive. It's going to say a line contains at least 2 points. A line contains at least 2 points. So our example on the right is showing some line L, and we're stating that it contains points P, Q, and R. So we might use the first postulate and this one in slightly different ways. Like for that first one, we might use that postulate to talk about the particular line that goes through 2 specific points. But for this third one, we might be already talking about a line, perhaps we're given some line to work with, and we want to then pull out a couple points to talk about. So I might say, well, let's say that point A is on line M. I know it's there because line M, or excuse me, A line contains at least 2 points. Okay, so let's look at some others. Well, this one's also going to sound a little bit repetitive. A plane contains, let's see, a plane contains at least 3 non-collinear points. And again, this might be like we're starting with a plane, and then we want to call out some points that we weren't immediately given on that plane. So we can point out, well, there's at least 3. In our example on the right, we've called out 4, in fact. Okay, the next postulate states if 2 points lie in a plane, then the entire line containing those points also lies in that plane. So the example is showing points A and B on plane K. What we're allowed to say is the line that goes through those 2 points, which we could call M, is also on the plane, and the entire line has to be on the plane. It's not one of those scenarios where the line is poking through. Okay. Next, if 2 lines intersect, then they do so in exactly 1 point. If 2 lines intersect, then their intersection is exactly 1 point. Now I want to sort of point out that these last couple postulates we've mentioned are phrased as conjectures. We've got our if, whatever, then whatever, right? Our if-then statements, conjectures. Now, the others could be rewritten in that same way, like the top one on the screen here right now. If a plane exists might be our hypothesis. Then it contains at least 3 non-collinear points. The other ones can be rephrased like that as well. And that might help us sort of see the difference between those ones that kind of sound repetitive. Okay, so we've got if 2 lines intersect, their intersection is exactly 1 point. We're never going to have a line kind of like bend around and come and intersect again, or 2 lines that intersect, but do so in like a plane. That's impossible. It's got to be in 1 point. Okay, our last postulate. If 2 planes intersect, then their intersection is a line. So if planes intersect, they intersect in a line. We'll never have 2 planes intersecting at just 1 point. It's always going to be a line. Okay. So these are our postulates. Now we're going to give some examples of using them. Again, you might try to challenge yourself to like immediately remember some of these statements. Maybe for these questions you want to have your list to refer back to. But do know that on our quiz, on our test, these are statements that you're going to want to have memorized. Maybe not the exact wording, but the ideas. Okay, so here's our diagram. It's a little bit easier to see when it's in color like this versus your note guide. I might suggest, if you're looking at that note guide and like having trouble making sense of it, maybe give certain things some color. Like you could go in and kind of call out different faces of our building. Like plane P is supposed to be this sort of like, I don't know, front of this building here. You could kind of like shade that in if you wanted. And same with this kind of, I don't know, diagonal sort of roof or whatever this is. That's also a plane. Okay, so you can give that some shading. So all these different sort of faces of the buildings are different planes. So I'm just going to maybe mention that. And I don't think the highlighting is super helpful on my screen, so I'm going to get rid of it. Okay, give yourself this practice. We want to state the postulate. Perhaps it's slightly rephrased in your own words, but we want to state the postulate in some way that can be used to show that these below statements 1 through 4 are true. So they are all true. Your job is to see how can you justify them using the statements the postulates. Okay, so pause the video. Otherwise, I'm going to go ahead and kind of reveal our answers. So number 1 is talking about points F and G. So I might point out to myself, where's F and G? F is here, G is here, along some line there. I guess it's line M per the top lowercase cursive letter. They lie on line M. Line M lies entirely on plane Q. So this is referring to if the points lie on a plane, then the line completely lies on that plane. So again, you might phrase it differently, but this is the postulate. If 2 points lie in a plane, then the line containing those points also lies in the plane. I think I might be missing the word like the entire line, but again, the phrasing can be a little bit different in your own words. Okay, next one. Points A and C determine a line. Determine a line or define a line. So A and C, to call them out, they're over here. You can see, sure, there's a line through there. How do we know, though? Well, we know because through any 2 points, there is exactly one line. Through any 2 points, there is exactly one line. This would not really be a case where I want to use the postulate that states, let's see, how else does it go? A line contains at least 2 points because we're starting with the points. We're starting with the points and we're getting a line as a result. So notice that kind of mirrors what's happening in the postulate. Through any 2 points, such as A and C, there is a line. They determine a line. So we kind of want to have that match up. Okay, number 3, plane P contains points E, B, and G. E, B, and G. So we can see they do indeed appear to be on plane P. And we know this is the case because a plane contains at least 3 non-collinear points. So notice again, we're not saying 3 non-collinear points define a plane. That's not what we're saying here. We're matching kind of what we're starting with. We have plane P. We're saying a plane has, and then these particular points, 3 non-collinear points. Okay. Lastly, line AB and BC intersect at point B. So it's giving us the specific intersection point there. We know that that is the case, and I might just take a tiny second to point out we really should have our little line symbols over here. Don't know why those are missing. Hopefully it's not missing elsewhere. In any case, we're going to use the postulate that if 2 lines intersect, they must intersect in a point. We know it's point B and not some other point because B, based on the name here, is clearly on both lines. So that's got to be the one shared point between the 2 lines. In other words, their intersection. Okay. So I want you to again take a moment to determine whether the following statements are always, sometimes, or never true. support your reasoning using a postulate. Okay, so go ahead and pause the video to give yourself that practice. All right, and I will go ahead and reveal our answers. Okay, number 1, if plane Q contains lines EF and EF contains point G, then plane Q contains point G. This is always going to be true. Justification is if 2 points lie on a plane, then the entire line containing those points lies on the plane. So we're saying point G, oops, if I had my highlighter up here, point G is on line EF, and since line EF is on Q, then G is also on Q. Okay. Next up, GH contains 3 non-collinear points. So line GH contains 3 non-collinear points. No, that can never be true. Non-collinear means not on the same line. So how is a line going to contain points that are not on the same line? That's impossible. So we said based on the definition of collinear, this is not true. Notice that's not actually a postulate. Our definitions that we've covered so far are also fair game. I should have mentioned that at the beginning, sorry. Okay, next, let's say plane A and plane B intersect in exactly 1 point. No, they cannot. Planes intersect in a line or they just don't intersect at all. Planes intersect in a line. Okay, point N lies in plane X and point R lies in plane Z. You can draw only one line that contains points N and R. This is always true through any 2 points, no matter if they're in different planes or not. Through any 2 points, there is exactly one line. Okay, we've got an extra little letter F there. Not sure about that. Okay. Moving right along, let's talk about the proof process. So the proof process. First of all, a proof just in general, so we introduced maybe a 2-column proof, but the proof in general is going to be a logical argument in which each statement is supported by a statement that we know to be true. And this is our justification, the statement that we know to be true. We'll call that our reason or justification, perhaps. All right, so that's just in general. We are specifically doing 2-column proofs in this class. Regardless, other proofs do exist, and they will almost always rely on deductive reasoning. Deductive reasoning is what we'll use to prove a conjecture. And a conjecture is, again, just that like if-then style statement in geometry. All right, now once a statement has been proven, it can actually be known as a theorem. So a theorem is going to be some kind of if-then type of statement, a statement of conjecture that has been proven. Perhaps we proved it, perhaps it's been proven by others and we're just using it. Sometimes we'll introduce facts and call them theorems, and we won't actually bother to write out the proof. For example, we know a squared plus b squared equals c squared, but we haven't necessarily proven that to be true. We're using it though. That is a theorem that we use. Oftentimes we'll prove them, but it's not like every single fact we bring up in geometry is something we're going to have to prove. No, just particular ones. Now, stuff we've proven in class or previously in our homework or whatever, we can then use them later on. So where our sort of bucket of reasons and justification is just really going to grow and grow and grow. Okay, so in general, we're going to follow these steps as we go through our proofs. We're going to first be listing out our given information, restating what we know in the beginning, And often this is going to be including a diagram. Diagrams are so helpful in geometry to get an understanding of what's going on, to perhaps recognize relationships between figures, drawing a diagram, or perhaps adding to a diagram that's already been given to us. Super helpful. Okay, then we're going to state what it is we're actually trying to prove. I'm going to state like, this is my end goal. It's kind of like your introduction paragraph in like, let's say English or whatever. You might have, here's my information and here's where I'm going with it. Then you have all those body paragraphs to support your argument. Here we're going to want to start by stating, this is where I'm going with this. And then later we'll get into the sort of body of the proof. That's step 3, creating a deductive argument. Now, I like to call out this piece. We're creating a logical chain of statements that are linked to each other. They're ultimately linked all the way back to what you were given, and then link all the way in the future towards what you're trying to prove. So they build on top of each other. Okay, each statement, of course, has to be justified. Some sort of reason has to be provided for why we know that is true. And those reasons can be, like we said earlier, definitions, perhaps algebraic properties, postulates, and theorems. The last step, again, I'm going to sort of liken this to writing an essay. You're going to restate what you just proved. So your last statement is always like, this is what I've proved, the end. And that's really similar to what you probably end up doing in English. Like, this is what I aim to do, and I did it. Okay. At an example. So before we move forward, I just want to note that the textbook does reference something called paragraph proofs, which is the same idea, just written like without our sort of 2-column format that we're going to be sticking with. We're not ever going to write paragraph proofs in this class. They are less formal, and they're just honestly a little bit more annoying to write. So we're not going to bother. Here's going to be our example, though, that we're going to write here together. We are given the information that AC intersects CD. So these 2 lines intersect. And what we're trying to prove is that ACD is a plane. Okay, so if you don't have one already, draw yourself a little 2-column big table where we're going to be listing out statements and reasons. Give yourself enough space to write some things in both columns. I also might draw just the simplest of diagrams. I'm going to draw my 2 lines intersecting. Now I'm going to label those lines. One of them is AC, so here's point A. One of them is CD, so I'm going to put point D. Notice I skipped point C. Think about where C should go. C's got to be here. Remember, we just kind of talked about this in one of the previous examples. C is in both names of these 2 lines, so therefore has to be the shared point in between the 2 lines. Okay, so basically that is a bit of information that I'm going to want to provide in my proof. Knowing that C is the intersection point is going to be really key. Maybe I'll make a note. I'm going to do a little brainstorming. C is the intersection point. I'm going to want to mention that. What else might we want to put in our proof here? Remember, we're trying to prove that ACD is a plane. So we might just perhaps remind ourselves that a plane is defined by 3 non-collinear points. So I'm feeling like we'll probably have to mention that fact at some point, that postulate at some point. I mentioned non-collinear in there, so maybe we can we state that A, C, and D are non-collinear? If we state that, we got to have a reason. Okay, so I see like C is on both lines, but A and D are on separate lines. Somehow we're going to have to mention that that means as a whole they're non-collinear. What else might be in our proof? Kind of feeling like that's a good brainstorm and that we might be ready to step through some things. Okay, first things first. Our first statement is always just restating the given information. And on one hand, this is always just like an easy way to begin a proof, is just restating what you're given. And it sets up what information we can use later in the proof. It's also definitely just worth a point when I'm grading proofs, so always include that. Next, step 2, what do I want to say? What about this fact that we know the intersection point has got to be C? We know that. AC intersects CD at point C. The reason I decided to provide there was one of our postulates, but you might notice it's restated a little bit. When lines intersect, they intersect at exactly one point. Gets the point across, right? But it's not necessarily the exact wording of the postulate. Okay, let's see. We know that they intersect at C. I'm wondering, do we have enough to say that they're non-collinear? Maybe we can mention that A and D are at least on separate lines first. A is on AC, D is on CD. I'm going to say the postulate there to justify this is that there's only one line through any 2 points. Only one line through any 2 points. So like D can't also be on AC or vice versa. So if we've established there in step 3 that A and D are on separate lines, and in step 2 we mentioned that their intersection is C. So we've like mentioned all these points. Well, as a group, I think we're ready to say those 3 points, A, C, and D, are non-collinear. So for my reason, I'm not exactly using a postulate. I'm not exactly stating a definition, but I am referencing a definition. I'm saying A and D are on separate lines, comma, the definition of non-collinear. Non-collinear means points not all on the same lines, or same line. Okay, well, we needed non-collinear in order to get back to plane, and I think we're ready for it. I think we're ready to say, well, if those are 3 non-collinear points, then they make a plane. And again, restating my postulate, 3 non-collinear points define a plane. Might not be the exact wording, but it gets the point across. All right, this is our first purely geometric proof. Give yourselves a pat on the back. We will work through some more in the future. Okay, thank you, everybody.